In this lecture, we will be starting with chapter 12, which is on periodic and trigonometric functions. So first of all, let's go back to the basics and discuss the definitions of the trigonometric functions as they come from the unit circle. So unit circle means a circle of radius 1. What we're going to imagine is that there's a point that travels around this circle. And what I would like to do is to be able to describe the position of that point on the circle in some way. The natural way that we think is natural because we're so used to it is to use the x and y coordinates. But the other way is to somehow use the circle to our advantage. So let's draw the point somewhere on the circle, let's say here. And instead of using, once again, its x and y coordinates, I'm going to connect this point to the center of my circle, and I'm going to think of the angle that this line makes with the positive x-axis. So this angle, let's call it theta, just to keep in touch with our Greek traditions here. What we're going to do next is actually just drop the perpendicular to the x-axis here and get ourselves a little right-angle triangle, this one right here. Now, once again, the coordinates of this point can be described as x and y in what we call rectangular coordinate system, or we can think of the coordinates of this point in terms of this angle theta. What the x coordinate will correspond to is what we call cosine of theta, and what the y coordinate will correspond to is what we will call sine theta. This is the definition of trigonometric functions, sine and cosine. The sine is the y value of the point, so the y coordinate, the height of the point on a unit circle. Cosine of an angle is the x coordinate of the corresponding point on the unit circle. So if we would like to annotate our little triangle here, again, the y coordinate is sine, which means that this height is actually sine of theta. The x coordinate is the cosine, which means that the horizontal distance here is actually cosine of theta. Now the angle is always counted from the positive x-axis counterclockwise. We have to pick a standard, and this is just the standard that we choose to work with. Now, I know that some of you would have seen the definitions of the trigonometric functions only from a triangle, but because they come from the triangle that lives in the unit circle, it's really useful to remember that, as it will give us a whole bunch of properties that are otherwise a little mysterious. So let's draw another unit circle here and talk about the signs of the sine and cosine. So as the point travels around the unit circle, let's say in this fashion, I can think about what sign, positive or negative, does it have in the various quadrants. So for example, if I have a point in the first quadrant here, let me actually make a point here, for example, somewhere right here, I can see that in terms of the x coordinate, it's going to be positive, and in terms of the y coordinate, it's also going to be positive. Now, the x and y coordinates correspond to sine and cosine, which means in the first quadrant, the cosine of any angle is positive, and the sine of any angle is positive, because the x coordinate is positive, and the y coordinate of any corresponding point in the first quadrant is positive. If I think of a point in the second quadrant, what am I going to get here? Again, let me actually pick a point. Let's say this one. In terms of the x coordinate, this point or any point in the second quadrant will have a negative x coordinate. X coordinate is cosine, which means that in the second quadrant, cosine is in fact negative. And then, of course, thinking about the y coordinate, this is above the x-axis, so the y coordinate will be positive, and the y coordinate is the sine, which means that in the second quadrant, sine is still positive. You can go through the other two quadrants in a similar fashion to discover that both sine and cosine here are going to be negative, and cosine will be positive here, but sine will be negative here. This, of course, gives rise to this all students take calculus, where this is just a shorthand for remembering that all the trig functions are going to be positive In the first quadrant, only the sine is going to be positive in the second one, and so on. There's no need to remember a mnemonic that is a little bit meaningless when all you have to think about is the unit circle and how the x and the y coordinate are actually the definitions of the trigonometric functions. The other thing that the unit circle gives us is the definitions of the other trigonometric functions. So once again, the sine is the vertical, the cosine is the horizontal, but this is for a triangle that lives inside the unit circle. What if I scale this one up and make it bigger? In particular, what if I extend it so that one side of it is tangent to the circle on this end, and the other side of it extends out and meets it somewhere up here? What I can see here is that this little triangle is actually similar to this big triangle, if you remember similar triangles from school. So what happens in similar triangles is that the ratios of the sides are actually the same. Now, I know that this one is what we called sine theta. This is what we called cosine theta. Now, what one might call this side, in fact, I think I inadvertently already called it that. This side is tangent to the circle, so that's exactly what we're going to call it. We're going to call it tangent of theta. Whereas this side crosses the circle, and in Greek, crossing is secant. So this whole side is going to be called secant of theta. In Greek, tangent means to touch. Secant means to cross. Now let's take a look at the similar triangles, this little guy and this big one. So what we can do is build the proportionality of sides. Let's say the vertical side to the horizontal side in each triangle. What are we going to have? Well, in the little triangle, the vertical side is sine of theta and the horizontal side is cosine theta. So sine theta over cosine theta. And because the triangles are similar, this ratio should be the same for the big triangle. The vertical side here is tangent of theta. Let me write that down. And the horizontal side is the radius of my circle. Now I know I'm working in a unit circle, which means that its radius is 1. So the horizontal side is 1. And we get a familiar relationship that tangent of theta is sine over cosine. Again, coming directly from the circle. Try to write down a similar proportion coming out from the similar triangles using the hypotenuse to see what the definition of secant will be. The other, among many other things that the unit circle gives us, is of course the equation of the circle itself. So let's recall from pre-calculus. What is the equation of a circle? Well, this circle is centered at 0 with radius 1. So the equation is going to be x squared plus y squared is equal to 1. Now remember that the x-coordinate is cosine, so I can replace the x with a cosine, and the y-coordinate is sine, so I can replace the y-coordinate with sine. And this will give me the familiar, what we call basic trigonometric identity. Again, coming straight from the unit circle. The other thing I can do to the basic trigonometric identity is, for example, divide everything by sine squared theta, or divide everything by cosine squared theta, which will give me a relationship between tangent and secant, or cotangent and cosecant. Try that to see how that works out. One last thing I will mention here that will come handy in the few applications shortly is the coordinates of points on the circle. In particular, remember that in our definition of the trigonometric functions, the point was traveling around the circle. It never left the circle, which means that no matter what point I pick on the circle, its x and y coordinate will always be within a certain range. Specifically, for the x values. For the x values, I can only go from -1 over here to +1 over here. So that means that my x is always bounded between -1 and 1. Similarly for y, the highest value for y is going to be for the point up here, and the lowest value of y will be for the point down here, which means that y is also trapped between -1 and 1. But of course, again, remembering that my x and y coordinates are actually sine and cosine of the corresponding angle, I can simply see that these relationships will hold for sine and cosine. And this is once again something that we see all the time. Sine and cosine are bounded between -1 and 1, but that is only because they come from the circle. One thing I forgot to mention is an interesting reference to the names of the functions. I talked about tangent and secant. What about the words for sine and cosine? Well, Greeks, which were the first to explore the actual concepts of trigonometry, ancient Greeks, the reason they wanted to study the motions around the circle of the points is because they were interested in celestial events. Now, Greeks were always very interested in symmetry, which means that they would actually examine double the triangle that we would look at, sort of mirroring this triangle further down. But once you draw a picture like this, it becomes a little more clear where the names come from. What does this look like to you? Just squint at it for a second and think, if you're an ancient Greek, what is this? Well, looks a lot like bow and arrow, doesn't it? And that's exactly where the names come from. Hypotenuse means stretched out. It's the stretched out part of the bow that you pull back when you want to fire your arrow. Sine, they actually thought of sine as this arc over here, and think of the word sine as we would use it in real life. We also talk about sinuses in our face, like our facial muscles or our facial features. Sine is this bent shape. This is the bent part of my bow and arrow. Cosine is actually just sine's friend, so that's where that name comes from. All of these names come from the unit circle, and the definition of all of these functions from the unit circle gives us all types of properties that are going to be useful throughout. Let's take a look at how we can use these definitions to our advantage to come up with the certain values for the different special points. We're used to thinking of the unit circle, or any circle in fact, as 360-degree rotation. However, the 360 degrees are a man-made number. This was just a number that was very convenient to use for the total degrees in a circle. It could have been very well anything else. Now, 360 is useful because it's both divisible by many things. For example, it's divisible by 4, which means every quadrant can be described as 90 degrees, but it's also close to the number of days in the year. And again, remember that Greeks actually studied this to study the motions of celestial objects, so to them, this was a very convenient number to have. However, again, this is a completely man-made number. The only unit of measure that comes from the circle is 1 radian. 1 radian is the angle made when we take the radius and wrap it around the circle. Let's see how that works. So this is my radius. If I can take this length and lay it down on top of my circle to the point where what I have is this sort of circular equilateral-ish looking triangle, then the angle made by this angle is exactly 1 radian. Let's draw this out. Again, you're not going to be able to do it exactly, but we can eyeball it where I would like to see that the length along the circle is the same as the actual length of the radius. So this is what we call 1 radian. Now, what if I continue around the circle? Where am I going to hit the next radian? Well, if I go this much and add about this much more, again, I'm completely approximating here, so I'm basically kind of hoping that this will work out. I would say that this is about where the second radian will be, and this is about where the third one will hit. So when I am at this point right here, I have 3 radians and a little bit more. Well, that's our familiar 3.14 and so on. 3 and a little bit more is exactly what we call pi. And if I continue around the circle in this way, I will notice that I'm going to get 6, and then a little bit more. 1, 2, 3, 4, 5, 6, and a little bit more. Well, that's 2 pi, or if you wish, approximately 6.28 radians. Right? This is where radians come from. So I know a lot of people are more comfortable dealing with degrees, but we will have to get a little more comfortable with radians. So let me annotate this second circle in terms of both. So we start off with 0, radians and degrees. We notice that what we have on the opposite side here is pi, which means that every quadrant is going to be pi over 2. So this is pi over 2. And then we can count in pi over 2's. 1 pi over 2, 2 pi over 2's, so 2's canceled and I just got pi. 3 pi over 2's, so 3 pi over 2's, and then here I'm gonna get 1, 2, 3, 4 pi over 2, or if I simplify, I'm going to get 2 pi. Now, of course, I can keep going around and around and around as many times as I want, and that again justifies why sine and cosine functions are in fact periodic, because the point on the circle here might correspond to the first time I hit it on my rotation, or the same point might correspond to me going around full circle once and then stopping on the second rotation around. In terms of other nice angles that we deal with all the time are the angles that are exactly halfway through the quarter, which means that it's pi over 2 divided by 2, or pi over 4. We also like the angles that split the quarter into, well, approximately 3s. This first angle is going to be pi over 6. The second one is going to be pi over 3. Again, I know that everybody is probably more comfortable with degrees, so let's write it down in degrees. 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, we have 180 at pi, we have 270 at 3 pi over 2, and then we have 360 all the way around. Now, the nice thing about, once again, remembering what the unit circle is and where the definitions of the trigonometric functions come from is it will allow us to calculate angle measures at particular angles very easily. So remember that the cosine of an angle is the x-coordinate at that angle. So it's the x-coordinate of the point at 0 degrees or radians, whereas sine is the y-coordinate at the point of 0 degrees or radians. So 0 degrees and 0 radians is this point right here. Its x-coordinate is the radius of the circle, and it's a unit circle, which means that this is 1. So the x-coordinate is 1, which means that the cosine of 0 is 1. The y-coordinate at this point is 0 because I haven't actually gotten any height to this point, which means that the sine of 0 is 0. This is where those special values come from. We can again then calculate this very quickly and very nicely at all of these sort of quadrant points. So for example, cosine of pi by 2 is going to be fairly easy to calculate, or something like sine of pi, or maybe sine of 3 pi over 2. Let's do a couple of these examples just once again to see how this works. Okay, so let's take a look here. Cosine of pi by 2 means I'm at the point where the angle is pi by 2. Cosine is the x-coordinate. So what is the x-coordinate of this point right here? Well, the x-coordinate is 0, which means that the cosine at that angle is 0. Next one I have here sine of pi. So this point right here that corresponds to angle of rotation pi. And sine is the y-coordinate. The y-coordinate of this point is 0, so I have 0. Let's take a look at another one. Sine of 3 pi over 2. So 3 pi over 2, this angle right here. Sine is the y-coordinate, which means I am at -1. And then, of course, you can also compute all of these types of angles with rotation. So here I have cosine of 7 pi. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. There we go, I finally landed. 7 pi is exactly the same as pi, and I'm looking for the cosine, which means I'm looking for the x-coordinate of this point right here, which is going to be -1. This can be further extended into the number of different applications. For example, how many solutions are there to an equation sine of theta is equal to some value, or sine squared of theta is equal to some value? Once again, if we draw a really quick sketch of our unit circle, we should be able to answer this question fairly quickly and easily. If sine of theta is equal to some value, remember that sine of theta is the y coordinate, then this is asking simply how many times does the y coordinate equal to this value on the unit circle. The y coordinate equals to a number means I am after a horizontal line here, so I can see that any horizontal line will intersect my unit circle in 2 points, which means that I have 2 solutions. If I have that sine squared is some value, that means if I take square roots of both sides, I'm allowing for positive and the negative of the square root, which means that I will be looking for positive and the negative corresponding solutions. So altogether, I'm going to have 4. I'm going to leave this one for you to practice what I finished the last slide with, to just read off the numbers directly as they are on the circle. We can also use the unit circle to justify why certain trigonometric identities are true and why some of them are simply not. So let me go through a couple of these. Here I have, again, let's say that this is a perfectly symmetrical unit circle. What the first identity claims, or it's not clear yet that it's an identity, what this expression claims is that the cosine of a negative angle, theta, is the same as the cosine of theta. Well, let's draw it out and see if we believe it. So let's say I have this as my angle, theta. Again, cosine is the x-coordinate of this angle. So the x-coordinate being this much. This is my cosine of theta right here. What would a cosine of minus theta be? Well, minus theta means I'm rotating clockwise, so I'm going to draw in the opposite direction. This is going to be minus theta. But now, of course, notice that if I am after a cosine, I'm still after the x-coordinate, so I'm after the exact same distance here. So yes, this is in fact correct. This is also what makes cosine what we say an even function. The minus gets absorbed, and the values of cosine of minus theta is the same as the cosine of theta. Go through the other expressions and see if you can justify why they're not, or why they are true or why they're not true. This is excellent practice to deal with the unit circle. The next thing we're going to talk about is how to produce graphs of sine and cosine from the unit circle onto the familiar rectangular system of coordinates. So let's start with the graph for sine of x, or let's actually call it sine of theta, and call this axis theta. Recall that sine of theta is the y-coordinate of the point on the unit circle as it travels around the circle. So I'm going to start here, which means that I'm starting at the angle 0, and the y-coordinate of this point is 0, which means I can put this point on my graph at 0, 0. We've noticed on the previous slide that I can, of course, mark all of the quadrant points, and those are something that I can calculate exactly, so I can put those points on my corresponding graph here. At the angle of pi over 2, which is right here, my y-coordinate, or the sine value, is going to be 1, which means the corresponding point is at 1. At the angle pi, which is here, the y-coordinate of the point is 0, which means my point is here. And then at the angle of 3 pi by 2, the y-coordinate is minus 1. So I'm going to have the graph here before I travel back up to 0 at the angle of 2 pi. And then if we generally think about how a point travels and what happens to the y-coordinate, you notice that first, in this first quadrant here, my y-coordinate, or the height of those points, increases from 0 to 1 fairly smoothly, and then it starts decreasing from 1 back down to 0. So this is what produces the familiar looking curve, something like this. And then, as my point travels from pi down to 3 pi by 2, I notice that the y-coordinate gets progressively bigger and bigger into the negatives until it reaches -1. And that's when I get this portion of the graph. Now, once I've completed the full circle, I know, of course, that my point can continue moving forward, which means, that this function will continue in the same exact manner. It will repeat itself. This is why these functions are called periodic, because I have one complete rotation, and then the exact same rotation and the exact same pattern repeats itself. So one period of this curve is going to correspond to this shape, which we actually call sinusoidal. For the graph of the cosine, the way to derive it is going to be very similar. Remember that cosine is the x-coordinate, so I'm going to leave this up to you to produce the corresponding points on the graph of the cosine and think about how the point travels around the circle and what that means for the x-coordinate as it goes from one quadrant to the next. Now, as we probably have seen in pre-calculus, sine and cosine functions can also have various transformations applied to them, which are the exact same transformations as applied to other functions. First of all, let me actually introduce brackets here because it will make it a little bit easier to actually describe what the corresponding C and D stand for. These transformations that I'm going to list work the same way for sine as they do for cosine. So first of all, the number that we're adding to the entire function will correspond to the vertical shift. Once again, there is nothing special about these transformations when it comes to sine and cosine. These are general function transformations. If we multiply the entire function by a number, this b, represents a vertical stretch. If that number is less than 1, it's going to correspond to the vertical compression, but we're going to call it a stretch and then think about whether it's actually stretching in the larger dimension or in the shorter one. For the trigonometric functions, this is also what we call the amplitude, because this will show us, as we will see on the next graph, how tall the graph of sine or cosine is. We know that generally sine and cosine function is trapped between -1 and 1. This will produce a wider range of y values. This C corresponds to a horizontal stretch, and again, you can think of that as a stretch or a compression, and this D will correspond to a horizontal shift, which for trigonometric functions is sometimes known as a phase shift. Because the functions repeat themselves, it's basically the same functions, but the phase of them have been shifted a little bit. So I've mentioned this word before already. These functions are what we call periodic. Generally, periodic functions are functions that repeat themselves, and which means that we can come up with a way to describe the smallest segment on which the repetition occurs. This is what we call a period. A period is, in fact, the smallest value, let's call it t, such that, and again, I'm going to define this for more general functions other than sine and cosine, but for any function f. So period is the smallest value t, such that f of x plus t is the exact same as f of x. So adding t into the input did not change the function. For the sine and cosine, the period is familiar to us, so period of sine and the period of cosine, the smallest value you have to add before the entire function repeats itself is 2 pi. And this is again clear from the unit circle. Now, if we apply a horizontal stretch to sine or cosine, of course the period will also be either stretched or compressed. So this C will stretch or contract the period, and the period will therefore be able to calculate as 2 pi over c. So let's remind ourselves that this is what the graph of general sine looks like. So notice that one period fits between 0 and 2 pi, and then it's the same curve repeated over and over again. So one entire period, let me highlight it here, is going to be between 0 and pi, and then this shape is repeated. What we're asked to do is to use the sketch of this function to come up with a general equation that represents that, thinking of how the transformations have been applied to, starting with sine of t, in this case, produce the graph that looks like this. So what are some of the things that we notice about this bottom graph? Well, first of all, the sine function being trapped between -1 and 1 is now actually ranging from -2 to 2, which means that its amplitude, or the vertical stretch, is equal to 2. Now, what about the period of this function? What we notice, of course, is between 0 and 2 pi here, the function only repeated itself once, that's why that's the period. But between 0 and 2 pi here, we see that the function has gone through a number of different repetitions. In fact, exactly 3 of them. Let's highlight each one. So I have one sinusoidal period, and then I have a second one, and then I have a third one, which means that the period has been contracted by 3. And then remember that according to my period formula on the previous page, my period is going to be 2 pi divided by 3. There have been no vertical or horizontal shifts. I can see that my graph is not shifted left or right or up and down, which tells me that C and D, something about C and D. And again, I'm just going to put the brackets around here because that's how we've defined C and D. So what can I do here in order to now notice the values for A and B? I've noticed that C and D essentially the A and D did not get affected, but I have an amplitude and I have a horizontal compression to then correspond to my new period. So altogether, I'm going to have that A, this one here, the vertical shift is 0. B, the amplitude is 2. So I have 2. I have that function is that of sine. And then the period is 2 pi by 3 because it repeated 3 times within the 2 pi, which means that my value for C is the bottom one here, which is 3. So then altogether, I have y is equal to 2 sine of 3t. Now, periodic functions occur in nature all over the place. For example, here we see the periodic number of sunshine hours that takes place over a year, or in the contrast of essentially the opposite, precipitation in millimeters that also takes place throughout the year, and the averages that will repeat themselves in the exact same pattern on average throughout years. We see these types of patterns in the high tides. Sometimes they're a little bit more irregular, and sometimes they're almost perfectly sinusoidal. We also see things like this in the body temperature, so that's something that occurs with a period of 24 hours, or the blood pressure, where it is a sinusoidal curve with just a little bit more complication added to it. We will model some of the realistic processes in lecture, but understanding where the trigonometric functions come from and how to construct them is essential. So if you need more background on the basics of the trig functions, also please take a look at the pre-calculus refresher course and the trigonometric module there. Here's a few more examples of working with the unit circle and seeing the relationships between sine, cosine, x, and y coordinates. The only thing you have to remember for all of these exercises is, once again, that simple definition that sine of an angle is the y coordinate of the point on the circle that corresponds to that angle, and cosine of the angle is the x coordinate of that same point on the circle. So with that in mind, I encourage you to try these exercises by yourself and do as many of them as possible to, again, get a handle on what a trigonometric function actually is. In terms of comparing, of course, you can use a calculator, but I encourage you to do it by hand so that, once again, you actually build the intuition as to how to work with the trigonometric functions. Now, for the next application, we're going to take a look at the various graphs that we can obtain from the experiments, and we're going to try to figure out if we can understand the pattern and match it to the situation that we have. So in this case, we have that the temperature of a chemical reaction oscillates between the low of 35 degrees and a high of 85 degrees. The temperature is at its lowest at time 0, and it reaches its highest in an hour. So we already have quite a bit of information about this temperature. We're then told that it gradually returns back to the initial temperature, which corresponds to the oscillation between the two values. Which of the graphs below best matches this reaction? So I encourage you to pause the video and try to think of each graph and try to figure out why it does or does not match the information in the question. So starting with this graph 1, the one piece of information that it does not match from the problem is the fact that at 0, the temperature here, it's not at the lowest, which is what we're told happens in our situation. So you cannot possibly beat this graph because, again, not lowest at 0. That's also the exact same reason why this next graph is not going to work either, because the temperature up here is also not lowest at 0. So I can, in fact, copy this over and eliminate this option for the exact same reason. Now, for this next two graphs, I can't use that logic because, in fact, the lowest temperature is at 0 here. What else do we have going for us? First of all, notice that this information, while kind of important if you were to draw the graph from scratch, isn't useful in eliminating any of the options because all of these all of these actually oscillate between the exact same two heights. You can see that the bottom and the top are the same. All of the scales are the same. So this information doesn't really help us eliminate any of the options provided. Now, we're also told that the highest point of the temperature is in 1 hour. So let's see here. This is 5 hours, which means that 1 hour is going to be 1/5 of that. And same here. Now, if the highest is going to be in 1 hour, then I'm looking at something like this on both of the graphs, and I can see that this graph matches, but this one certainly does not. So this is my other piece of information that I can use to eliminate this option, not highest at 1 hour, and that leaves me with the only viable option, which is this third one here. This kind of observational techniques and eliminating of the options is helpful, not of course in just the multiple choice questions, but in the questions where you would have been asked directly to construct such a graph. Taking all of the properties of the function and then producing a reasonable graph of it is a really great skill to have. For this next question here, we're going to think about the sunspots on the sun. So sunspots are essentially solar storms that happen on the surface of the sun, and we know from observations that they fluctuate approximately on 11-year cycles, with the highs of 120 and the lows of 0 sunspots detected in any particular year. So here we are told that in year 2000, we've actually detected the peak of 120 solar storms, and therefore we're able to produce a trigonometric oscillating function that will model the number of expected solar storms. Here are the 5 different options for such a function. And once again, I encourage you to pause the video here and try to figure out which of these functions actually matches the description in the problem. As in the previous problem, I can actually use the lows and the highs to eliminate the different possibilities. So I was told that the low is of 0 sunspots detected, so my lowest point overall has to be at 0. And this first function here, if you graph it or if you simply analyze it, let's take a look. The smallest the sine can be is -1. So this whole thing, the smallest value it can take is -1. 120 times -1 is -120. 60 minus 120 is -60. So this is not lowest at 0, which means that it cannot possibly be this. I cannot have -60 solar storms on the sun. For the rest of them, you will notice that the coefficients add up so that if this value of a trigonometric function is -1, then I'm going to end up with 60 minus 60 in all the cases, and that will produce the 0 as the lowest possible. Now, looking at my 4 remaining options, I noticed that these coefficients in these two are not quite the same as these two. And of course, if you remember from the general form of the trigonometric function, these coefficients correspond to the period. Now, we are told that the period is 11-year cycles. So that means that I need to see 11 years cycle repeat over and over and over again. That means that my period is going to be 2 pi over 11, which of course leaves me with these two options and eliminates these two. So here my period has eliminated the two options. And now I'm only down to 2. What other piece of information haven't I used yet? Well, I haven't used, for example, the fact that in year 2000, we have 120 sunspots that have been actually observed. So what I can do is plug in 2004t and then see what happens. And you will notice that sine of 0 is going to be 0. So this whole expression is going to become 0. And therefore, the overall value here will be 60. Now we're told it has to be 120, so it can't be this option. And just to be on the safe side and actually check to see whether this even works at all, just because it's the last option doesn't mean that it's viable, cosine of 0 is going to be 1. So I'm going to end up with 60 plus 60, which is 120. So given all of the information that we do have, I can see that this last value indeed matches my information. Now, the other way to ask similar questions is to give a graph and then ask to produce the actual function form. Once again, this is only reliant on the general form of the function, and it is a pre-calculus skill. So please pause the video and see if you can approach these questions by yourself. So what we have here, first of all, notice that we're asked to write this in terms of sine. It doesn't really matter, sine or cosine, because they are really just shifts of each other. If we're going to work with sine, then what we're going to think about is sine goes through the origin. So if the graph does not, it means that it was shifted left or right, corresponding to the fact that it really should begin here and then carry on as the sinusoidal curve afterwards. The next thing to notice is observe where do we see the period. And so in this case here, I can see that this curve will constitute my entire period, right? This is one time repeat, and then it keeps going in that shape over and over again. I went from 1 minus 2 pi to 1, which means that in this case, my period is indeed 2 pi, which is the period of the sine as it is. And now all I can see is that really, instead of starting at 0 here with my curve, there we go. This would have been what I want, but I am shifted over 1 unit to the right. So this is actually going to be sine of x minus 1. That way, if I plug in 1, I get sine of 0, and therefore that is in fact then my corresponding x-intercept. And using similar logic, we're gonna go through the other two graphs. So let's see if we can spot the full cycle here. Well, the full cycle goes from 1 to 3 here. So my period between 1 and 3, these are physical numbers. My period is actually equal to 2. There's no pi involved, so I'm going to have to work with that. So that means that what I will have as the coefficient c in the sine is 2 pi over 2. Next up, I also noticed that, of course, if I am going to have this as a sine function, my sine goes from 0 and up this way. So that means that I am once again shifted over, and I'm once again shifted over in the exact same way. So what I actually have is x minus 1 as my shift. And the last bit that I still have to incorporate is the fact that my graph doesn't go up until 1. My graph goes up until 1 over pi. So that is my amplitude, and therefore it has to appear in front of my entire function. Doing the exact same thing on the last graph. Let's say for this one, we're going to model it with cosine, just to mix it up a little bit. Here then, I have to think of my period as being of this shape and repeating over and over and over again. If you want to model it with sine, you're going to start, let's say, here and have this like sideways S-looking thing. With cosine, you have to go from the top back to the top. Okay, so once again, it goes between 1 and 3, so my period is still 2, and therefore, if I'm modeling with cosine, I will have 2 pi over 2 inside. I notice that with cosine, I would have started at 0 up at 1 here as well, so I am still working with a shift, and my amplitude is 1/2, so I have to incorporate that into my entire thing as well. Okay, modeling with trigonometric functions is quite easy once you get the handle on them, but coming up with formulas based on the graph is something that certainly requires quite a bit of practice. In terms of actual processes, let's take a look at a real model here. So in Abbotsford, the shortest day is going to be approximately 8 hours of light, and it's going to occur around December 22nd. Whereas the longest day is going to be approximately 16 hours of light, and it happens around June 21st. What we're asked to do here is approximate this cyclic process by using the sine function. So first of all, because it is easier to work with things once we visualize them, let's sketch a rough graph of what this function actually looks like. So we know that this process repeats through the year. So my cycle is going to be, if we're working with days, 365 days long. I can see that my lowest daylight is 8, my highest is 16, and exactly halfway through is going to be 12. So we can start at 12 hours, which is the spring equinox. We're going to move up to 16 hours of daylight in the middle of the summer, or at the first day of summer, not middle of summer, right? So this is going to be my June 21st. We're then going to fall all the way down to the 8 hours of daylight on December 22nd, and then move back up into the 12 hours for the spring equinox. Okay, so what we have here is this part of the sine curve that will repeat over and over again throughout the years. So first of all, it's easy to notice that the period of this function is 365 days. And so I have to incorporate that into my function directly. Then the amplitude is, of course, something that I have to also take care of. It's not 1 here. In fact, this graph you can see is shifted entirely off of the x-axis to be a little higher up, but the amplitude is between 8 and 16. So the amplitude is actually 12 plus 4 and minus 4. And I'm going to have to take care of that. So I have 12 plus minus 4 hours. And that means that my vertical shift is actually 12. And my amplitude, so the height of the function itself, is actually going to be 4. Now, the starting and the end points is also something that I really have to think about. So I'm going to assume that it starts here on March 21st or September 21st. It doesn't really matter whether it's a spring or fall equinox, but it has to start at one of those, just so that basically here I'm allowed to fix my starting point, and I'm going to fix it so that this most closely resembles the sine function, and I don't have to shift it horizontally as well. Okay, so I'm going to assume, for example, that this is going to be March 21st, the spring equinox. And then I can put all of this together into a function. So my vertical shift is 12, my amplitude is 4, my function is sine. Now I have to make sure that my period is 365, which means that I have to introduce 2 pi over 365 as a multiple inside my actual sine function. And because I didn't have to shift anything horizontally, I simply will have t as the variable here. You can, of course, double check that this makes sense. The period is computed as 2 pi over whatever this coefficient is. And so if I write that down as a function, I can see that I will flip and multiply, resulting in 365 as my final answer for the period of it. Now, for the last set of examples in this lecture, let's take a look at sketching. So instead of having a graph to start with, we're going to start with the function and try to produce its graph. So first of all, I have sine x multiplied by 1/2. In all of these, the first step is to think about what the function that has not been modified in any way will look like. So for example, in this case, I'm going to start with the sine. So I'm only going to draw one period of it. This is my sine, so this is 2 pi. Remember that 1/2 outside of the sine function means that it's going to be its amplitude that gets affected, but the inside has not been modified, so the period is still the same. So that means that I am simply going to make my function shorter on both ends, but the period will actually stay the same. So my blue function here is my 1/2 sine x. For the next example, what I have is still 1/2, so I still have my amplitude being 1/2, but now I also have 2 pi as the multiple in the inside, which means that my period has been affected. So my period is 2 pi divided by whatever this coefficient is, which is also 2 pi, and therefore my period becomes simply 1. So now if I am to produce a one cycle of this function, my amplitude is 1/2, my period is 1, and that means that in between here and here, I have to be able to fit one full cycle of a sine function. So something like that. I'm going to try to keep it quite symmetric. There we go. That's not half bad. Remember that it is fully symmetric vertically. So amplitude of 1/2 means it goes between 1/2 and -1/2. Now for the last example here, most complicated of all, what I can see is I have 1/2 as the amplitude, I have 2 pi as a period, and of course now I'm also introducing some kind of horizontal shift. So first things first, I actually have to remember that in my general form, the function looks like this, where c is the period and then d is the horizontal shift. So before I can even move on, it's probably best to actually simplify the function. I'm going to factor out 2 pi from that. So I'm going to have 0.8 pi divided by 2 pi here, which of course, if I simplify this further, will end up being 0.4. Okay, so now that means that on my graph, I have my amplitude is 1/2, so my graph is only going to go up to 1/2. I have 2 pi as a factor, so my period will be affected in the same exact way. So my period will still be 1, but now my function is going to be shifted 0.4 to the left. So what I'm going to do is actually, I'm going to draw the exact same graph I drew above. So this is my original graph of 1/2 sine of 2 pi x, and then I'm going to shift everything 0.4 units to the left. So something like this. So let's say this is 0.6, this is going to be 0.4, and my function is going to look like this. So this is my final transformation of my sine function. As I said before, sine, cosine, all of these trigonometric functions are very useful in various applications, but it does take quite a bit of time to get a hang of them. So do exercises to make sure that you understand how to go from the formula to the graph and from the graph to the formula. And I encourage you to take a look at the pre-calculus refresher modules as well to boost up your trigonometric practice skills.